told you before that the most important differential equation methods you probably learn in first order differential equation techniques is linear equations and separation of variables. The other ones are all additional tools in the handyman's box that use once in a while, but mostly use the two basic rules. Today we're going to do probably the most important rule for second order differential equations. It's homogeneous linear differential equations with constant coefficients, and we'll do the second order method. And actually these are the most important for third and higher order also. So after first order, this is the method you really want to know. It comes up in lots of engineering and physics applications, for instance. Lots of other methods too, particularly things with vibration in them. And so these are equations of this form. Last time we talked about homogeneous differential equations of second order with continuous coefficients. We put d squared y dt squared plus p of t times dy dt plus q of t times y equals 0. That was the standard form. This time, or we can put the a2 and a1 and a0 here and have all coefficients. But those were linear equations with continuous coefficients. More specifically, suppose they're constants. Suppose you have a times the second derivative plus b times the first derivative plus c times y equals 0, where a isn't equal to 0 or it's first order. These are second order homogeneous equations with constant coefficients. Constant coefficients is obvious. Second order because it's second derivative. Linear because it's of this form that we said last time, right? Something times d squared y dt squared plus something times dy dt plus something times y. And then homogeneous because the right hand side is 0. So that's how all that name comes about. Now how do we solve these things? There's a nice way of kind of having an intuition for this. You notice sometimes by plugging in, if you plug in e to the right constant times t, maybe you can get a solution. So let's try that. Suppose I did a trial solution or a test solution, books call them sometimes. E to the rt, where r is a constant, plug it into here and see what happens. So I plug it in for y, and let's see then y prime would be, right, derivative of e to the rt is r e to the rt. Remember that by the chain rule, if you take the derivative e to the rt, it's think of that as e to the u times derivative of u, and derivative of rt is r. So that's where that comes from, is the chain rule for e to the rt, taking u equals rt. And then if you take the derivative of r e to the rt, you just bring another r down and get r squared e to the rt. And then we'll plug all those into here. So we've got a, and the second derivative is r squared e to the rt. B times first derivative is r e to the rt. And c times e to the rt for y equals 0. So e to the rt will be a solution if and only if this is true. Now we can divide by e to the rt, it's not 0, and we get ar squared plus br plus c equals 0. So you see that e to the rt is the solution to the differential equation if and only if r is the solution of this quadratic equation called the characteristic equation for this differential equation that's homogeneous with constant coefficients. Now, remember from algebra how to solve a quadratic equation. There's three different cases, right? You could have distinct real numbers, r1, r2, that both satisfy this. You have equal real numbers, r1 and r2, that both satisfy this. Or you can have complex conjugate numbers. Complex conjugate alpha plus I beta, alpha minus I beta. Those are the conjugates, plus and minus. We'll show them below. And those are the three cases. Well, since the quadratic formula breaks up into three cases, according to the solutions of quadratic equation are given by the quadratic formula, which breaks it into those three cases, it makes sense that then the solutions to the differential equation must break into three cases, right? Now, there's suppose, let's say greater than 0. Let's see if I can fix that. If b squared minus 4ac is greater than 0, then the quadratic formula for this, remember minus b plus or minus square root b squared minus 4ac all over 2a from algebra. if this is greater than 0, then there's two real solutions of the characteristic equation. And so e to the R1t and e to the R2t are solutions of the differential equation, right? If you get R1 and R2 are solutions of this quadratic equation, we said the corresponding solutions are e to the R1 and R2 times t. Now, are they independent? So you take the Wronskian, recall, to check independence of solutions of a second order equation with continuous coefficients. We plug e to the R1t, e to the R2t into the Wronskian. You put those on the first line, their derivatives on the second line. Take this times this minus this times this. That's what this determinant lines mean. And you get R1 minus R2 times e to the R1 plus R2t, right? This times this is R2 e to the R2t. And then you subtract this, R1 times e to R1 plus R2t. And that's not 0, right? If R1 and R2 are not equal, then this isn't 0. And e to anything isn't 0. So the Wronskian is not 0. Consequently, these are independent solutions whenever R1 and R2 are distinct real solutions of the quadratic formula that has the same coefficients, a, b, and c, as the differential equation. Now, suppose b squared minus 4ac is equal to 0. Now, R1 is equal to R2 is equal to minus b over 2a. That's the quadratic formula where you got square root of 0 here. Right? That's how you get R1 and R2 equal. That means this is a solution by our derivation above, but R2 is also equal to e to the R1t because R1 and R2 are equal. And so there's only one independent solution. You put those into the Wronskian. I didn't write it out, but you'll get 0 out of that if you put in the same functions of the first line. And so what do we do? Well, it turns out you can try this. Plug in t e to the R1t. We'll be able to derive why that works later. But for now, we'll say, suppose you plug this into the differential equation, and it turns out it's also a solution. Now you put it into the Wronskian, and it turns out that the Wronskian is not 0. And so this is an independent solution when this is. And so, remember from last time, the general solution of the differential equation, given two independent solutions, is an arbitrary multiple of one plus an arbitrary multiple of the other. So when R1 and R2 are distinct solutions of the characteristic equation, this is the general solution, C1 e to the R1t plus C2 e to the R2t, because those are independent solutions. And when R1 equals R2, you have to do it differently. You have these two independent solutions, e to the R1t, t e to the R1t, and you take C1 times 1 plus C2 times the other for that one. Finally, the hard case is suppose b squared minus 4ac is less than 0. Now, you get complex conjugate roots out of the quadratic formula. Maybe remember, right? If this is less than 0, then you get square root of a negative in the quadratic formula. And so you get some number, it's minus b over 2a, plus I times another number, which is square root 4 minus 4ac minus b squared all over 2a. That's just out of the quadratic formula. And now what do? Well, we just proved that e to the R1 times t and e to the R2 times t are solutions, so how can that be? They're imaginary. Well, they're solutions if you allow imaginary functions, right? Functions. If you figure this out, this has an imaginary part, and it is a solution if you take derivatives of complex functions, but that's not very consoling to your boss who says, where did the airplane fly? Well, it flew into this imaginary number. Not so good, right? So these are actually solutions. Complex valued solutions means they have an imaginary part as well as a real part. What if we just want only real solutions? We can say, remember from last time that any superposition solutions of C1 times 1 plus C2 times the other is again a solution for these homogeneous problems, right? So let's try that. Suppose we take y1 plus y2, these complex valued solutions with imaginary parts in them, and add them together and divide by 2. This is 1/2 times the one plus 1/2 times the other, so it's a superposition of them or a linear combination of two of them. And That means you have this plus this over 2. Well, if you use the property that e to the alpha plus I beta is t is e to the alpha t times e to the I beta t, you can rewrite it like this. You can factor in e to the alpha t out of both of these and pull it out front, and now you've got this. But now you've got to remember Euler's formula. E to the I times a real number beta times t, another real number. E to the I times, let's call it theta, is cosine theta plus I sine theta, where theta is beta t. So e to the I beta t by Euler's formula is complex exponential to an imaginary number function. Gives you cosine beta t plus I sine beta t. Now similarly, e to the minus I beta t, it's just the same thing with minus beta t instead. So it's cosine minus beta t plus I sine minus beta t, but in the sine, remember it's an odd function, the minus comes out. Cosine minus beta t is the same as cosine plus beta t, so the minus goes away, it's an even function. So, long story short, Euler's formula that e to the, I should write it down. This function that e to the I theta is cosine theta plus I sine theta. There's Euler's formula for what the exponential of an imaginary number should be. And we just applied that here with theta equal beta t and got this for e to the I beta t and this for e to the minus I beta t from that. Alright, now we can also find out from that, because the I sine beta t and the minus I sine beta t cancel, we're just left with cosine plus cosine all over 2. Well, 2 of these over 2 is just cosine. So when we add y1 and y2 and divide by 2, we just get e to the alpha t cosine beta t. So what? It looks more complicated, but it's real, right? Alpha and beta are real numbers, and so this is e to a real number times t cosine real number times t. This is a real valued function that is also a solution to the differential equation. Now similarly, if we take the two solutions, e to the alpha plus I beta t and e to the minus I, e to the alpha minus I beta t, and subtract them and divide by 2I. Well, what do we get now? Again, e to the alpha plus I beta t becomes e to the alpha t, e to the I beta t, and you factor the e alpha t out of here, and same thing here. Write it like that. And now this one by Euler's formula is cosine beta t plus I sine beta t. E to the minus I beta t, recall, is cosine minus I sine. But this time we're going to subtract them and divide by 2I. Well, when we subtract them, the cosines cancel. And we've got I sine beta t minus the minuses plus another I sine beta t is 2I sine beta t over 2I gives sine beta t. So we got e to the alpha t and all this, by a little algebra, is just sine beta t. And so this one we just showed is also a solution, because remember, any linear combination, a multiple of y1 plus a multiple of y2, where y1 and y2 are solutions, is again a solution. So we took 1 over 2i y1 plus minus 1 over 2i times y2. It has to be a solution by that superposition principle. So this is a solution, just like this one, it's real valued. If you put these into the Wronskian, you'll find out these are also independent. Let's not do the extra work. But here's two independent solutions to the differential equation. Solutions because they're, right, e to the RT. We got them from e to the RT being a solution. And then we took linear combination solutions to get solutions. So the bottom line is that if you get complex conjugate solutions, b squared minus 4ac is less than 0 for the characteristic equation, then this will be the general solution of the differential equation. C1 times one solution that we derive with difficulty plus C2 times the other solution we derive with difficulty. C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t is now the general solution of the problem. So there's three different cases, and look how easy this is. When you see a second order differential equation with constant coefficients, a y double prime plus by prime plus cy equals 0, all you do is write down the quadratic equation with the same coefficients a, b, and c, ar squared plus br plus c equals 0. Solve it by the quadratic formula to get two solutions, r1 and r2, or that might be equal. They might be two distinct real numbers, in which case you immediately write the solution c1 e to the r1t plus c2 e to the r2t. They might be equal real solutions, in which case you immediately write the solution c1 e to the r1t plus c2t e to the r1t. Or they might be complex conjugate solutions of the characteristic equation, in which case you immediately write down the solution c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t, where alpha is the real part of the solution of the quadratic equation, and beta is the imaginary part. In other words, you get alpha plus I beta as a solution by the quadratic formula. Let's write some examples down. This will make more sense. Here's an initial value problem, a differential equation together with two initial values, that y of 0 is 1 and y prime of 0 is 7. So we're going to solve the differential equation by this method, and then we're going to plug in these values. And what happens when you have initial values is it also then determines the constants. This is an infinite number of solutions, right? All three of these are, because there's two arbitrary constants that can be any real number each. That gives all solutions to the differential equation. If you also give an initial value for y and an initial value for y prime, that determines the two constants. And you can see y pretty easily if you've taken linear algebra before. But these will always determine a unique solution out of the infinite set of solutions that you get with C1 and C2 arbitrary. So here's this differential equation. d squared y dt squared plus 4d y dt plus 3y equals 0. Together with those initial values, you write the quadratic equation with the same coefficients. 1, 4, 3 is r squared plus 4 plus 3 equals 0. We solve it. We can solve it by the quadratic formula, or in this case, it's easier, just a factor, right? This factor is r plus 3 times r plus 1 equals 0. So r equals minus 3 or r equals minus 1 are the two solutions to this. Quadratic formula give you the same results as factoring. And so two solutions to the differential equation are y1 equals e to the first number times t, e to the minus 3t, y2 equals e to the second number times t, minus 1 times t. Those are independent solutions since r1 and r2 aren't equal. The general solution immediately, look how nice this is. c1 e to the minus 3t plus c2 e to the minus t, that's all solutions to the differential equation. Now, we also had initial value. This is an infinite set of solutions. C1 and C2 could be any real numbers. And by the way, I should mention, if you are solving for complex valued solutions, that's a perfectly legitimate thing to be doing too, as long as you're mathematicians, right, you can get imaginary solutions. This is still the general solution over complex valued functions. The rules are exactly the same. You just let C1 and C2 be arbitrary complex numbers. So they have a real or imaginary part. And the same thing in all of these, right? This is the general solution over all real valued functions. It's also the general solution over all complex valued functions if you just let C1 and C2 be complex numbers, arbitrary complex numbers. So you let C1 and C2 be arbitrary real numbers, you get all real solutions. If you let C1 and C2 be arbitrary complex numbers, you get all complex valued solutions. Once in a while, those are of interest, particularly in mathematics. So here's the solution over all real functions, if C1 and C2 are said to be arbitrary real numbers, or over all complex valued functions, if C1 and C2 are allowed to be complex numbers. Let's do the real case. That's what we're interested in primarily. Once we have this, we plug in, well, let's calculate the derivative of it. The derivative of this, right, e to the RT has derivative r e to the RT, so it's minus 3 e to the minus 3t is the derivative of this term, all times C1. And derivative e to the minus t is minus e to the minus t. That all multiplies C2. Here's the derivative of our general solution to the differential equation. Now we can plug in y of 0 equals 1. That means we plug in 1 for y and 0 for t here. We get 1 equals c1 e to the 0 is 1, plus c2 e to the 0 is 1. So this is c1 times 1 plus c2 times 1 equals 1. That's the initial condition, is just one linear equation in c1 and c2. Now we'll plug in y prime of 0 equals 7 using the derivative of our solution. So we put in 7 on the left here, equals minus 3 times c1 e to the 0 minus c2 e to the 0 is minus 3 times c1 times 1 minus c2 times 1 gives us minus 3c1 minus c2 equals 7 from the left side, another linear equation. We've got two linear equations in two unknowns. Because the Wronskian is not 0, it automatically follows that the determinant of this side isn't 0. And if you took linear algebra, that means this always has a unique solution. So that's the nice thing about these. We will get a unique solution every time, as long as we wrote down the correct general solution, when we put in initial values. Y at 0 equals a number, and y prime at 0 equals a number, or you can, it's still called initial values. It doesn't have to be at t equals 0, as long as these are the same value of t. Two values, one for y and one for y prime, any numbers whatsoever for the right-hand side, will determine a unique solution always. So how do we solve two linear equations and two unknowns? We can either solve for one of these, like c1 in terms of the other, c1 equals 1 minus c2, and substitute into the other, and that works, so you can find c1 and c2. If you get more than two equations, the usual way they do it is faster than that for lots of equations, is to add multiples of one equation to another. They call that elimination in linear algebra, or Gaussian elimination is a special form of that always, an algorithm that always does elimination to the solution. So let's add 3 times the first equation to the second. Even easier. Add the first equation to the second makes the c2 and the minus c2 cancel, and then c1 plus minus 3c1 gives minus 2c1, and 1 plus 7 is 8. So I add the first equation to the second, I eliminate c2, and I find out that c1 is minus 4. Now I can substitute c1 equals minus 4 into either equation. Let's plug it in to the first one. That's the simpler equation. So minus 4 plus c2 equals 1. And I just get c2 equals 5. There's the unique solution. c1 is minus 4, c2 is 5, and the general solution with those numbers put in gives minus 4 e to the 3t plus 5 e to the minus t is the unique solution to the initial value problem. So just like our first order equations usually took one initial value, a very nice problem, it always took one initial value, to get a unique solution out of the set of all solutions. Now, for these, we get a unique solution always out of two initial values, one for y and one for y prime, at the same value of t. There it is. Here's the sketch. Of this initial value problem solution. If you draw what this looks like, you notice these are both decaying exponentials, but one's positive and one's negative. And what happens is the one with the less negative exponent decays slower, right? E to a very negative number decays times t decays faster than e to a smaller number times t, a less negative number times t. So here's what it looks like. And then for t getting negative, both those blow up, get arbitrarily big in absolute value. So the function, if you sketch it, looks like this. This is where a graphing calculator is nice. You can just have it draw the thing and see what it looks like. But there's our unique solution to the initial value problem. Here's another one. Let's try this one. Y O prime plus 4y prime plus 4y equals 0 together with these initial values. Y of 0 equals 1, y prime of 0 equals minus 1. Real simple ones. What do? We write down the characteristic equation with the same coefficients. 1r squared plus 4r plus 4 times 1 equals 0. What are the solutions to this? This factor is r plus 2 times r plus 2, or you can use the quadratic formula. And you get two equal solutions. R1 equals R2 equals minus 2. Right? So this means there's only one independent solution, e to the minus 2t, and the other e to the r2t is the same solution, only one independent. So we said the second independent solution is t times the first one, t e to the minus 2t. And the general solution is c1 times e to the minus 2t plus c2t to the minus 2t. An arbitrary linear combination of the two independent solutions when the solutions of the characteristic equation here are equal. And sometimes it's kind of nice to group these, right? Algebraically, this is c2t plus c1 all times e to the minus 2t. That gives you a little more insight what the graph looks like. Now we can apply the initial value, initial conditions. Y of 0 equals 1, so we put 1 in for y and 0 in for t, and we get c1 e to the 0 equals 1, says that c1 has to be 1. If we take the derivative of this, there's a product rule involved, but we get this, minus 2c2t minus 2. I think there's a c1 missing there, maybe. No, minus 2c1 plus c2 e to the minus 2t. And we plug in the second initial condition, y prime of 0 equals minus 1. So we get minus 1 over here equals all this stuff over here. Says that y prime of 0 equals minus 1 on the left equals minus 2 plus c2. And so c2 equals 1. And we get this unique solution, y equals t plus 1 e to the minus 2t, because c1 and c2 are both 1. So there's what that one looks like if you plot it up. Finally, the other case, suppose you get complex conjugate solutions. Here's one, y double prime plus 2y prime plus 26y equals 0, together with these initial conditions. The characteristic equation is 1r squared plus 2r plus 26 times 1 equals 0. Now, this one doesn't factor using real numbers, right? If you take b squared minus 4ac, you'll see that discriminant is negative. You know immediately it doesn't factor. But if you apply the quadratic formula, you'll get these two solutions, minus 1 plus or minus 5i. Two complex conjugates. We call minus 1 the real part. We call 5 the imaginary part. The imaginary part is a real number that multiplies I. And so alpha is minus 1, beta is 5. And we deduce then from what we wrote above, e to the minus 1t times cosine 5t, e to the minus 1t sine 5t are independent solutions of this differential equation. So we write down immediately the general solution. C1 times the first solution plus C2 times the second independent solution is just C1 e to the minus t cosine 5t plus C2 e to the minus t sine 5t. You can factor the e to the minus t out of here and write it like this, which is kind of suggestive. We're going to shortly show why this is really neat. This actually turned out, remember your trig really well, be a single sine wave. You can write this as a single sine function of 5t plus a phase shift and multiplied by an amplitude. And so this is actually a sine wave times a decaying exponential. That tells you what the solution looks like. You like the picture of it for that reason. But first let's find out what C1 and C2 are. Putting in y of 0 equals 1 gives this. You're putting in 0 for t, sine of 0 is 0. Put in 0 here, cosine of 0 is 1. So you get 1 times C1 times e to the 0 equals the right hand side 1. So that tells you that C1 equals 1. Then you take the derivative, find out it's this. Now you take the derivative of this, and here it is, it's this mess, and plug in the second initial condition, that y prime of 0 equals 4. So that says that 4 equals all this stuff with 0 plugged in. It's 4 equals minus 1 plus 5c2. Right? Sine of 0 is 0, and this falls out. Cosine of 0 is 1. So there's your 0 plus 5c2. And plug in 0 here. Cosine is 1. I'll put the minus in front. And e to the 0, 0. Anyway, so you got this equation by plugging in 0 for t and minus 1 for y prime. That tells you that C2 equals 1, and consequently y equals e to the minus 2 times 1 cosine 5t plus 1 sine 5t. just plugging into here, C1 and C2 equals 1 on this problem. Well, now, what does this come out to look like? If you use trigonometry to combine these, you can write cosine 5t plus 5 sine 5t as square root 2 sine 5t plus pi over 4. That's just trigonometry. We'll talk more about that later, actually. And you can rewrite this in the alternate form, square root of 2 e to the minus t sine 5t plus pi over 4, which tells you it's a sine wave times a decaying exponential that begins with this amplitude, that begins with this magnitude at t equals 0. And there's its graph. What you have is the square root 2 e to the minus 2t multiplying the sine wave. Looks like this, and this is minus that value. And because sine oscillates between, this is the solution we just found, the blue, and these are guidelines for drawing it. If we draw the guidelines at the thing that multiplies the sine function, we find out that the solution oscillates between square root 2 e to the minus 2t and minus thereof, like that. So there's a nice way to draw the solution when you have complex conjugate solutions to the characteristic equation. These problems on the homework are like that. Some of them have distinct real solutions to the characteristic equation. Some of them have equal, and some of them have complex conjugate. These, you just write the general solution, C1 times one solution plus C2 times the other. And there's just 3 cases for everyone that you have to consider to be able to solve all of these. These are the same thing, except you also plug in the initial values afterwards to determine C1